let's see. Okay. Oh, Sandy. Hi, Sandy. How do I do this?
Hi, Mel.
Hi, yeah. Thank you. Okay. Beamer. Share. All right, that's a start. Okay, so is this visible? Is Beamer?
This is a log file.
We see the text file.
Sorry?
We see the text file, but not the Beamer presentation. We're seeing the text file.
It's not the text file, it's the log file.
Log file.
See the log file?
Yeah.
No. Let me go. Share.
Log looks good.
Text shop, Beamer, PDF.
Ah, there it is.
Bingo.
Oh, okay. All right. So what I am about to discuss would be cutting edge mathematics in the 19th century, probably even known in the 18th century. But it's just a curious question that came up, and I mentioned a little bit of it last week. It came up in connection with the proof of the Boudin-Fourier theorem, and it has to do with interactions between the zeros of a polynomial. So let's see. So I'm going to be talking about multiplicity matrices and multiplicity vectors. So just to fix, oops, why is it? It went to page 14. I can't figure this out. Let me see if I can go. This is page 1. Page 2. No, damn. Oh, that's right. Okay. The multiplicity vector of a polynomial. So we have a non-zero polynomial f of x, and this is just to fix our notation that lambda is a 0 or a root of the polynomial of multiplicity mu, at least 1, if you can write f of x as x minus lambda to the mu times some polynomial g, and g of lambda is non-zero. And if f of lambda isn't 0, that is if lambda is not a root, then we say lambda is a root of the polynomial of multiplicity 0. And I'm interested in the following question. So you take a polynomial of degree n, and this is the fj of x is the jth derivative of f of x. So for all lambda, any real number lambda, and any j, you let mu j be the multiplicity of lambda as a 0 of the jth derivative. And mf of lambda, this is the multiplicity of lambda as a root of f. So mu 0, mu 1. So lambda is a root of f of multiplicity mu naught of the first derivative of multiplicity mu 1 and so forth. Of course, the nth derivative of a polynomial of degree n is a non-zero constant. So mu n is always 0. So we call this the multiplicity vector of the polynomial at lambda. And this multiplicity vector is the 0 vector if and only if lambda is not a root of any of the derivatives of f. So this is the multiplicity root of the polynomial. Again, I have no doubt that everything I'm about to say was investigated 100 years ago or more. It's just that I don't know where or by whom. So this is all stuff that is I do during the commercials on BBC, I guess. So for example, if you take this cubic polynomial, here are the derivatives, and what are the multiplicity vectors? So if you let lambda equal 0, 0 is the root of f of multiplicity 2, of f prime of multiplicity 1. It's not a root of the second or third derivative, so it's multiplicity 0. So the multiplicity vector for 0 is 2, 1, 0, 0. If you take x equal 1, you can see just from the factorization, it's a root of multiplicity 1 for the second derivative and of multiplicity 0 for the other derivative. So the multiplicity vector is 0, 0, 1, 0. If you look at x equal 2, it's a root of the first derivative and no others. And this is the multiplicity vector. Look at x equal 3, it's a root of the function, but none of the derivatives. And for any lambda other than 0, 1, 2, or 3, lambda is not a root. So the multiplicity vector is just 0. Here's another example, slightly more interesting. If you take this quintic polynomial, by some miraculous reason, I can factor it. And for example, if you just look at 0, lambda equals 0, it's a root of multiplicity 3 for f, 2 for f prime, 1 for f double prime, and 0 for the remaining 3 derivatives. And so you get 3, 2, 1, 0, 0, 0. And if you take lambda equal 1, it seems to be a root of f. It's not a root of f prime, but it jumps back in again to become a root of f double prime, and then it's no longer a root. And so one of the curious things, if you look at these multiplicity vectors, is like, say it's a polynomial of high degree, so you have a lot of derivatives, like a certain number might be a root for a while, and then it's no longer a root. And then it decides, and this is being a root, so it comes back in and it's a root again, and that process just sort of cycles through. It's just kind of cute.
It's interesting to ask for which polynomials all the roots of the second derivative are roots of the original polynomial. Yeah, I mean, if you obviously they can't, you can't have the same roots of the polynomial and its derivative unless there's multiplicity. But suppose you have a polynomial with all the roots are different, and all the roots of the second derivative appeared as roots of the original polynomial.
Okay, so
up to scaling, it's a unique polynomial.
right. So yeah, that's a good question to keep in mind, because something like that will come up later. Let's see. Okay, so let's just recall Taylor's formula, which says if you take your polynomial and you expand it in powers of x minus lambda, the Fourier coefficients or Taylor coefficients are essentially the derivatives evaluated as lambda up to some positive factor. And in particular, the nth derivative is always of a polynomial of degree n, it's just n factorial times the leading coefficient, so it's never 0. Okay. So these are just a few simple lemmas that there's nothing here that you couldn't do in like your Calc 1 class. So that f of x be a polynomial of degree n, and fj is the jth derivative. So it has degree n minus j. And you have a 0 of order mu j at x equal lambda, if and only if mu j is the most n minus j. That's the degree of the polynomial. And if you look at the next mu j consecutive derivatives, they're all 0 until you get to the j plus mu j derivative. That's different from 0. This is just a restatement of the fact that if you have a root of multiplicity mu for a function, it's a multiplicity mu minus 1 for the derivative. That's all it is. Let's see, what does this say? Suppose you have a polynomial of degree n and a real number lambda, and you let mu j be the multiplicity of lambda as a 0 of the derivative. So this is the multiplicity vector for f at lambda. So if mu j is not 0, if it's greater than or equal to 1, then j is in most n minus 1. All that says is that mu n has to be 0. So if mu j is not 0, then j is not n, it has to be most n minus 1. And as you go from mu j to the next term in this vector, mu j plus 1, the value decreases by 1. Again, this is just the fact that if a function has a root of multiplicity mu, then its derivative has a root of multiplicity mu minus 1. So let's say that a multiplicity vector is a vector whose coordinates are non-negative integers, where the last coordinate is always 0. And whenever a mu j is at least 1, the next term is exactly mu j minus 1. And the theorem says that every such vector is the multiplicity vector of some polynomial of degree n. So, and you can do this in various ways. I had done this originally by a different kind of construction. Moshe Newman pointed out last week that you can, it's enough just to look at the coefficients of the Taylor series. So if f of x is this polynomial with the Taylor expansion at lambda, a necessary and sufficient condition that a multiplicity vector, mu naught up to mu n, be the multiplicity vector of this polynomial with lambda, is that the coefficients of the polynomial are 0 if and only if mu j is not 0, if it's 1. So what this says is that every multiplicity vector is the multiplicity vector of some polynomial. What does this say? Vector of non-negative integers. Maybe it just says the same thing. I'm not sure why it's repeated. The vector, yeah. Okay. All right. So multiplicity vectors are easy because whenever you have a multiplicity vector, it is the multiplicity vector of a polynomial at some particular point lambda. But it's more interesting perhaps to ask about how zeros of a polynomial can interact with each other. So I take a polynomial f of x of degree n, and fj of x is the jth derivative. So j goes from 0 up to n. So you have n plus 1 different j's. I take a set lambda of real numbers, distinct, and it doesn't matter how I order them. So for simplicity, I just put them in strictly increasing order. So I have n plus 1 real numbers. And for each lambda I, right, I goes from 0 to n. For each lambda I, let mu ij be the multiplicity of lambda I as a root of the jth derivative. Okay. So if I fix I, I'm just looking at the multiplicity vector for that lambda I, but I'm doing it for all the different lambda i's. And what I will call the multiplicity matrix of f with respect to the set lambda is this n plus 1 by n plus 1 matrix of the mu ij's. So for each I, the ith row in this matrix is the multiplicity vector of the polynomial f evaluated as lambda I. So this is some pretty matrix of non-negative integers. Of course, the last column has to be 0. And so on. So there's some information in here in this matrix, whatever it might be. Well, so for example, if I take the polynomial x to the 4th minus 4x cubed plus 4x for whatever reason, and I take the set 0, 1, so they're just 2 lambdas, so there's just 2 rows in this matrix. This is the multiplicity matrix. So if you look at 0, 0 is a root of f, and it's a root of the second derivative of f, but it's not a root of any of the other derivatives. But 1 is a root of the third derivative only. So, yeah. Okay. So the definition of the mu ij as a multiplicity means that for every j, what do we know about the jth derivative? We know that lambda I is a root of multiplicity mu ij. The lambda i's are different. So this polynomial is divisible by this product. So it's this product times some other polynomial g sub j, which is not zero at any of the lambda i's. And because, so this is the jth derivative of a polynomial of degree n. So its degree is n minus j. Now, from this expression, you see that the sum of the mu ij's, j is fixed, you're summing over I, is certainly less than or equal to the sum of the mu ij's plus the degree of g sub j, because this is equal to fj. So the degree of this polynomial is exactly n minus j. So we have this inequality on the entries of the multiplicity matrix. This inequality for fixed j, I goes from 0 to m. This is a column sum. So this says if you take the jth column sum of the matrix, of a multiplicity matrix, it's bounded above by n minus j. Just one other quick comment. For any non-zero polynomial f, multiplying f by a non-zero constant doesn't change the zeros of the function or its derivatives. So the multiplicity matrix of f and of cf are the same. So in particular, you can save yourself some paperwork by only considering monic polynomials with the leading coefficient. So let me define an m by n multiplicity matrix. It's an m plus 1 by n plus 1 matrix of non-negative integers, where, first of all, each row is a multiplicity vector. That means wherever you have a positive coordinate, the next coordinate to the right is strictly one less, and the last coordinate is 0. So independently of each other, each row is a multiplicity vector. And we also have this constraint on the column sums. For each j goes from 0 to n. The sum of the elements in the jth column is in most n minus j. So this is a multiplicity matrix. 1, 3 means, unfortunately, a 2 by 4 matrix. Right? By the way, I've enumerated these things, but this is a multiplicity matrix. Whenever there's a positive number, the next number is one less, and it always ends in 0. But, why is there a but? This is not a multiplicity matrix. Why is it not a multiplicity matrix? Well, the condition on the columns, this column adds up to 2, right? 1 plus 1 is 2. This is row j equals 0, j equal 1, and n is equal to 2. N minus j in this case is 1, and 2 is not less than 1. So that's sort of like the numerical statement. But if you just think for a second about what this means, this has to be the multiplicity. If it's the multiplicity matrix of a polynomial, it has to be quadratic, right? Because the degree is 1 less than the number of columns. So there's a quadratic polynomial. The first derivative is linear, but according to this, the first derivative has 0 as a root and 1 as a root. So the first derivative would be divisible by x times x minus 1. You can't have a linear divisible by a quadratic. So this is not a multiplicity matrix. The rows are multiplicity vectors, but this is not a multiplicity matrix.
I'm not sure about 0 as a root and 1 has a root. It has two different values, lambda 0 and lambda 1 is a root. But you haven't specified that lambda 0 is 0 and lambda 1 is 1.
Oh, so first I'll show you in a moment. It doesn't matter, but
Yeah, for only
I
two
don't-
lambdas.
actually, but it really doesn't matter because this says you have two different numbers, lambda 1 and lambda 2. They're both roots of the linear polynomial, and that's not
Right,
possible.
right, sure. Sure, but I mean, in general, you don't specifically want your lambdas to be 0, 1, 2, and so on.
Correct.
Yeah.
Okay, so there are two simple problems to state. Suppose you have a multiplicity matrix, and suppose you have a strictly increasing sequence of m+1 real numbers. Does there exist a polynomial f of x of degree n such that your multiplicity matrix is the matrix of this polynomial with respect to lambda? So that's the first question. And the second question, which is somewhat less restrictive perhaps, suppose you have a multiplicity matrix. Does there exist a polynomial of degree n and some increasing sequence of real numbers for which your multiplicity matrix is the multiplicity matrix of f with respect to lambda? So for the second problem, you're not restricted to a fixed set of lambdas. Is there any set of lambdas for which your matrix is the multiplicity matrix? So these are different problems. Neither of which I can solve.
Yeah, I don't understand problem 2 still, right? You begin by saying let M be a multiplicity matrix, and then you ask, is it a multiplicity matrix?
Excuse me?
So in the second problem, it seems like you begin by saying let M be a multiplicity matrix, and then you're asking, is it a multiplicity matrix at the end?
No. So there are two different objects. There is the multiplicity matrix of a polynomial with respect to a set of numbers lambda.
Okay.
On the other hand, there is a multiplicity matrix, which is a matrix where the coordinates are non-negative integers that satisfy the two conditions that whenever one is positive, the next one is one less. And there's this constraint on the column sums. So if you have such a matrix, the question is it the matrix, is it the multiplicity matrix of a polynomial? That is, for example, this is a multiplicity matrix, but I don't know a priori that there exists a polynomial in two numbers for which these are the sets of multiplicities of the polynomial and its derivatives.
Okay.
That's the question. Let's see. But let's try to see if we can solve a problem. So here is a multiplicity matrix. And let's take lambda to be the set 0, 1. So I want to see if this is the multiplicity matrix of a polynomial. So there are 4 columns, so it would be the multiplicity matrix of a cubic polynomial. And I can assume that it's monic. So what does that mean? So let's suppose that this is the multiplicity matrix of some cubic polynomial. So in that case, the first row will be the multiplicity vector with respect to 0 for that cubic. And the second row will be the multiplicity vector with respect to 1 for that cubic. So what does it mean to say that this is the multiplicity vector for the cubic? So you have a the zeros in the vector give you the non-zero coefficients in the polynomial. So a 0 here means that the cubic term has a non-zero coefficient, which I can make 1. A 0 here means that the quadratic term has a non-zero coefficient. Positive numbers here means that the linear and constant terms of the polynomial are 0. So this polynomial has to be of the form x cubed plus ax squared. Right? That's what this tells us. Now, this is the multiplicity vector of f of x at x equal 1. So this will tell us something about the coefficients of f when you expand it in powers of x minus 1. So what this says is you'll have non-zero coefficients for the cubic, quadratic, and constant terms. So with respect to x minus 1, f of x will look like x minus 1 cubed plus b times x minus 1 squared plus c. And even I hope I did it right, but even I can expand the cubic. So you get this. So f of x looks like this, but it also looks like this, but it's the same polynomial. So these have to be equal, which means you can equate the coefficients. So a, the quadratic term, a is equal to b minus 3. The linear term has coefficient 0. So 3 minus 2b is 0. The constant term over here is 0. So b plus c minus 1 is 0. So I can solve these equations, a, b, and c, and this is my polynomial. So this is the expansion around 0. This is the expansion around 1. And you can check, or if you can't, you can use Maple or Mathematica to check that these are equal. So this matrix, this multiplicity matrix, is the multiplicity matrix for 0 and 1 for a cubic, and it's actually up to, so long as a, then this is the unique monocubic, this works. Okay. Oh, this is fun, actually. I enjoy doing this. I enjoy doing these calculations. Let me try another one. This is a little more complicated. So I call this M prime only because I call the other one M. So you can check, I hope, that this is a multiplicity matrix. There are 5 columns, so this would be the multiplicity matrix of a quartic polynomial degree 4. If I take 0 and 1 as the set of values, this first row is the multiplicity matrix for the polynomial with 0. And the second row, just as before, is the multiplicity matrix for the polynomial f1. So this tells me when I write the quartic in powers of x, it's going to be x to the 4th plus some constant times x cubed. This says when I write the polynomial in powers of x minus 1, it's going to be something x minus 1 to the 4th and x minus 1 squared in the non-zero constant term. So this is just what I said, that with respect to 0, the polynomial is x to the 4th plus ax cubed. And with respect to x minus 1, it's x minus 1 to the 4th, b times x minus 1 squared plus c. And in the tour de force of high school algebra, I can even expand the 4th degree binomial, and I get this. So f of x equals f of x. When you equate them, you get this equals this. So when you compare coefficients, you see a has to equal minus 4, b plus 6 is 0, 2b plus 4 is 0, b plus c plus 1 is 0. I don't need all of that information, but if b plus 6 is 0, b is minus 6. But if 2b plus 4 is 0, b is minus 2. So we've proved that minus 6 equals minus 2. So you have 2 choices. You can either say, okay, we have proved that minus 6 equals minus 2, Or you can say that's absurd. And therefore, the assumption that that matrix I wrote down is the multiplicity matrix of a polynomial is false. So let's just go back and look at the matrix again. Here it is. I mean, it's a completely beautiful multiplicity matrix. It's not that big, not that complicated, only has 2 rows. But in fact, at least for 0, 1, this is not the multiplicity matrix of any polynomial. And in fact, as I will show in a moment, it's not the multiplicity matrix for any set of 2 numbers. Sorry, Moshe, did you have?
I was just about to say what you were about to say, yes.
Right. Okay. So how can you tell, looking at the matrix, whether it is the multiplicity matrix for a polynomial or not? I mean, I can think of absolutely no reason why Isaac Newton would not have thought about this in, I don't know, 1742 or so, and probably solved it. But I can't, I mean, I don't know why. I can't tell by looking yet. Actually, I kind of, but there's some secret reason I'll explain in a moment. But there's some obstruction to this being the multiplicity matrix of a polynomial. Okay. Okay, this is just an observation that here we have a multiplicity matrix that lambda naught be the set of the first m+1 non-negative integers. Let lambda be a set of m real numbers that form a strictly increasing arithmetic progression. So the statement is that there is a monic polynomial f0 of x of degree n, for which this is the multiplicity matrix with respect to 0 to m, if and only if there is some other monic polynomial for which this is the multiplicity matrix with respect to lambda. And the proof is straightforward. So if you have your arithmetic progression of the lambdas, there's some delta positive, if these are increasing. The lambda I is lambda naught plus I delta. So if f naught is a polynomial of degree n, for which that matrix is the multiplicity matrix with respect to the numbers 0, 1 up to m, then the jth derivative has this form, right? This is just the definition of multiplicity. And just define the polynomial f of x to be f0 of x minus lambda naught over delta. So f0, oops, sorry, cross out the word monic. I should have put a delta to the end of front. But this is a polynomial of degree n, and f0 of lambda I minus lambda naught is, what is it? It's I times delta over delta is I. So f of lambda I is exactly f0 of I. And you just double check how the derivatives function. None of this is particularly exciting, but the jth derivative of x has lambda I as a root of multiplicity u sub ij for all I and j. That means that matrix M is the multiplicity matrix for f with respect to lambda. So, and conversely, if you had a monic polynomial of degree n, for which the matrix was the multiplicity matrix with respect to lambda, defining f0 of x to be I delta plus lambda naught. I left out an x, so this should have been x delta plus lambda naught, I guess. This would give you a monic polynomial of degree n, in which m was the multiplicity matrix with respect to 0, 1, 2 up to m. So this says that if you have a multiplicity matrix with respect to the first initial segment of integers, it's also a multiplicity matrix with respect to any arithmetic progression of the same length. Now, arithmetic progressions don't normally come up, except when you have two numbers, because every set of two numbers is an arithmetic progression. So as a corollary of that result, it says that when you're only looking at sets lambda with two different values, where you're evaluating the polynomial, what's true for any set is true just for 0 and 1 and conversely. So that's why when I'm looking at just these two row matrices, I only have to consider 0 and 1.
A different normalization I've run into in connection with orthogonal polynomials, you can always assume that lambda 0 is -1 and the last of the lambdas is 1. So that all the lambdas occur between -1 and 1.
Right.
It's a sort of favorite interval for orthogonal polynomials theory.
Yes. It says whenever you have two numbers, they form an arithmetic progression. That's not true. Oh, okay. So what's more interesting than constructing a polynomial for which a given matrix is the multiplicity matrix is to have some way to understand the obstructions to a matrix, the multiplicity matrix, being the multiplicity matrix for a polynomial. So here are two examples which come just from looking at the counterexample that I had done explicitly a few minutes ago. So here I take a multiplicity matrix. There are two variables, 0 and 1. And it's a matrix for a and it would correspond to a polynomial of degree n if there were such a polynomial. There are n+1 columns in this matrix. And I don't care at all about the first n-2 columns, but the first row ends 2, 1, 0, and the second row ends 1, 0, 0. And I claim that there exists no polynomial of degree n, of course, for which this is the multiplicity matrix. Why? You want to know. So suppose there is such a monic polynomial of degree n, for which this is the multiplicity matrix. So let's just look. What does this say? This says that if you look at, when you evaluate that polynomial with 0, you get this multiplicity vector.
So Mel, can I interrupt for a second? So this multiplicity matrix means that the last column adds up to at most 0, and the penultimate column adds up to at most 1, right?
Correct.
And then the column before that should add up to at most 2.
So let's see. So n minus j is 1. Yes. Is that right? I hope it's not. If it is, this is not a very interesting example. Yeah, so actually, thank you. So this is not a multiplicity matrix. So let's try this one. That other one I attacked on just before the talk started, but you're right. But let's look at this guy. So this is a multiplicity matrix because the sum of the entries in the n-j column is always at most j. So 0, 1, at most 2, at most 3, that's okay, and so forth. Actually, yeah, yeah, this is a multiplicity matrix. I assume this is not the multiplicity matrix of a polynomial. Why not? So this says that if you were to evaluate the polynomial at 0, you get this multiplicity vector. You will have an x to the n term, an x to the n-1 term, and then the next term that might appear has degree at most n-4. So f of x as a sum of powers of x, you have an x to the n term, an x to the n minus 1 term, no n minus 2 or n minus 3, and then other terms, these coefficients can be 0 or positive, doesn't matter. So this is from looking at the first row of the matrix. When you look at the second row, this says you have x to the n, not x to the n minus 1. You have x to the n minus 2, but not x to the n minus 3, and whatever else there might be. So when you expand this in powers of x minus 1, you have x minus 1 to the n, no n minus 1 term, n minus 2, no n minus 3 term, and whatever else there might be. And when I start to expand this second line, I think I get x to the n. That's the coefficient, that's the power of x to the n. The only power of x to the n minus 1 is minus n x to the n minus 1. For n minus 2, I get n choose 2 x to the n minus 2, and bn minus 2 x to the n minus 2. For the coefficient of x to the n minus 3, I get minus n choose 3, and n minus and minus n minus 2 vis of n minus 2. So this is this. But so you see here, in this expansion, I have x to the n minus 2 with this coefficient, and x to the n minus 3 with this coefficient. But those coefficients have to be 0. So I get that bn minus 2 has to be minus n choose 2. And bn minus 2 also has to be minus n choose 3 over n minus 2, which is equal to this. So these two numbers have to be the same. And that doesn't happen too often. That's impossible. So no matrix of this form can be the multiplicity matrix of a polynomial. Okay. And there are more examples of shapes of matrices that don't work, but I don't know how to classify. So let me just repeat the two open problems I mentioned a few moments ago, because these are obvious questions to ask. If you have a multiplicity matrix and a set of numbers, lambda 0, I should have started doing lambda n. Is there a polynomial for which your multiplicity matrix is the multiplicity matrix of the polynomial? Or if you want to give yourself more freedom to choose the lambdas arbitrarily, if you only have two variables, it doesn't matter. It's 0, 1. Whatever works for 0, 1 works for any other numbers. But can you find a set of numbers and a polynomial for which the multiplicity matrix is the multiplicity matrix of f at lambda? When you start looking at 3 or more variables, 3 or more places where you're evaluating, things are much stranger. Someone could ask, for example, take the set 0, 1, 2, and 0, 1, 3, construct a 3 by n plus 1 matrix such that made a multiplicity matrix, which is the multiplicity matrix for some polynomial f with respect to 0, 1, and 2, but not with respect to 0, 1, and 3 for any polynomial. And more generally, this is sort of the, whatever you want to call it, but it's somehow to describe. So what we're describing somehow are forbidden interactions between roots of polynomials. And that's what I'm trying to figure out here. So, so if you state the problem like this, describe the forbidden interactions between roots of polynomials, that has a sufficiently Zen aura that you can come up with many different ways to think about it. Anyway, that's the story. Thank you for your attention. Get out of that. Okay.
So those first two problems that you gave, you don't know the answer for m equals 2?
No, I don't know the answer for n equal 2. And I don't know. So what that says is that in my definition, so I started off with the definition of a matrix, of a multiplicity matrix, just as a matrix where the rows had to be multiplicity vectors. But then I saw there was also a condition on the columns. So I added that to the definition. But that still isn't sufficient to guarantee that the matrix comes from a polynomial. So, so what would be very nice if one could find, you know, a small number of additional conditions on the matrix that would be necessary and sufficient for there to exist a polynomial which generates that matrix of integers.
I'm pretty sure you can find something for 2 rows. I very much doubt that you could find something in general.
I don't know.
There's a counting question here too. Just like how many of these multiplicity matrices are there?
How many are there? Well, I mean, so you can't have, yeah, I mean, there are some counting questions, but you can't have a root of multiplicity more than n. And in general, the set of all the multiplicities of all the roots at for the jth derivative can't be more than n minus j. That's my column condition. And it may be if you can find some other counting condition that just gives us something to add to the definition of multiplicity matrix to reduce it. Right? I mean, that's the idea. I mean, I have to say that I've thought very hard about it this week because I never thought about it until last week. And this week it is competing with the news, which means that I have even less time than I normally would. But it is an interesting question. Somehow I can't believe that, as I said, that Isaac Newton didn't think about this, you know, in the 18th century. But in any case, I don't know the answer at all. I have no idea. But,
here's another intermediate question for you. Can you find a matrix which will be the multiplicity matrix if you reorder its rows, but not if you keep the order? That is to say, you were saying at some point, does it, you know, you order the lambdas and you weren't sure that it matters, but it might matter. It might be that, you know, things with high multiplicity can only appear at the ends, let's say, or, you know, that sort of thing.
Yeah.
I don't understand.
Okay, so to
You're
each
saying reorder the rows, but not reorder the lambdas.
precisely.
Oh,
Keep the
okay.
lambdas ordered and reorder the rows, or if you like, you know, leave the rows and reorder the lambdas, whichever you prefer.
Right. Yeah. Yeah. So that only makes sense for 3 or more variables.
Sure. And in fact, I think it might only make sense for 4 or more, because for 3 you can sort of, oh no, actually the middle and the ends. Yes, it does make sense. Yes.
Yeah. No, but even the case for 3 seems extremely difficult. I mean, 2 is hard enough for me at the moment, but 3 just seems very hard. And you know, there's been a lot of work recently about zeros of polynomials. For example, I had sent out to everyone on the mailing list the paper on the whatever the jazzed up version of Lamar's conjecture that you can't have, for a non-cyclotomic polynomial, roots can't be too close to the unit circle. That has a slightly different flavor, but It's not completely different. And somehow this has to do with I mean, you're forbidding some configurations of roots of a polynomial and its derivative simultaneously. And, I don't know how to express that.
Along these lines, there is a question that perhaps it's a naive question, but if one were to go back to the Buddha-Fourier theorem and consider an interval between A and B, and I construct a matrix with 2 rows. And in the first row, I put the values, not of the derivatives, but the values of the Euclidean algorithm remainders evaluated, let's say, at A, and in the second row, evaluated at B. I get the impression that there must be some internal restrictions to the type of things that you can get with the assumption that we are now making sign matrices with a plus, a minus, and a 0 if it's a 0 at one of the points. And I'm just wondering, I mean, this is probably something you might have thought, that there are some internal restrictions as to what type of matrices can arise. But it's something to play around with some small polynomials. And for some crazy reason, I feel that the derivatives may not be the natural things to look at, but rather these other objects that arise in the Buddha-Fourier theorem, where you have the sequence of, I mean, they are closely related, but not, one is more sensitive to the other as to locations of zeros.
Yeah, I mean, so what led to this was that, you know, in Boudin-Fourier and then Sturm also, you're looking at sort of sign variations for at a fixed x, and then letting x vary from A to B, and that the number of sign variations always drops. But when you try, but the way you prove that it drops by an even integer as you cross a 0 of one of the derivatives has to do with looking at the way the multiplicities work out. So you get this multiplicity vector somehow involved in that. And so you have some like, so you have this smoothly, sorry, x is varying smoothly from A to B, and but at each x you have this vector of integers, and it obviously can't, a vector of integers can't move smoothly. It has to, if it changes, it's a jump. But how it does is, I mean, that's sort of what's involved in this somehow. At least that's what led to this, trying to understand how that counting the number of sign changes as you move across the interval behaves.
Yeah, there is an interesting and related question that is suggested by a remark of Klein, I think in his elementary elements in mathematics, where he takes, for example, the discriminant of a cubic polynomial. So this is a polynomial, the discriminant depends on 3 variables, and he looks at the surface or the region that this defines, places where it's positive, where it's negative, and so for a cubic polynomial, you can more or less say if your polynomial has all real roots, then the coefficients have to lie in this region. If it has 1 real root and 2 complex conjugate roots, then it has to lie in this other region. And so probably in a more general context, this sign matrices or the multiplicity matrices are describing some regions that are somehow controlled by the values of the I don't know, the elementary symmetric functions. I mean, it's hard for me to visualize what's going on, but certainly an interesting question. There are restrictions. There are definitely restrictions.
It's actually
so, for instance, this is
in the computer science department at City College, a Russian guy whose name I can't remember, who knows a lot about polynomials. And I would sometimes invite him to give a talk in the seminar, and his general reaction, he doesn't seem to answer emails, so. But but he really does know a lot about polynomials. He did a lot of work with the Vigderson and
What?
that.
Are you talking about Victor Pan?
No, he's my
Oh,
colleague at
right.
Lehman. This is a guy-
Sorry, I missed the first part. Sorry.
no, he's a guy at City College. What is his name? Yeah, I just can't. Anyway,
The other question that arose, this is again a triviality, but when you start with a polynomial, we were asking us to, can it share roots with its second derivative? If you go in the other direction, each time that you take a polynomial, you integrate, you bring in, there is an indeterminate constant floating around. So, and if you do it 2 times, then you have 2 constants, and you can certainly induce those constants to be in such a way that they share perhaps 1 or 2 roots and so on. So in general, if you take a certain number of integrations, you pick up a variable that you can assign, and you can certainly say things about how many roots are shared by a polynomial and its jth derivative and so on. But I'm wondering whether those are the only restrictions. There may be other situations where you could, for example, for a polynomial and its second derivative, it's true that what will restrict its sharing of 2 roots? Could it share 3 roots, 4 roots? I mean, that's possible, but I'm wondering what restrictions arise.
Well, if you have all but 2 roots, obviously they can't share all the roots. If you have all but 2 roots shared, it completely determines the polynomial up to scaling. It's, you solve it as a linear system with, you can get all the coefficients exactly.
Right.
The more zeros you require to match up, the more, it just adds linear equations.
Right. So it's a well-determined.
I've never fiddled with the case of multiplicities, but when all the zeros are distinct, it's very straightforward.
Right.
You get the same sort of setup as with Lagrange polynomials, Chebyshev polynomials. So you get a differential equation. I'm talking about the case where all but 2 roots agree. It belongs to a family of things called Gegenbauer polynomials. Spherical, ultra-spherical polynomials, something like that.
I also thought of this as a kind of a discrete dynamical system, that if you take a very high degree polynomial and you start to differentiate it and look, and you say, well, here's 0. Suddenly 0 is suddenly a root. And then 1 becomes a root, and then it's no longer. And then 0 comes back, and then 1 comes back. And these things pop in and out. And, for 1 fixed value of lambda, you can have however exotic behavior you want occurring. But if you're trying to do 2 things at the same time, it's just interesting to try to understand how the appearance and disappearance of 0 and 1 as roots behaves.
Or you could look at a transcendental function and look at the zeros of all its derivatives.
Yeah, but that's getting hard.
Well, actually, in some ways, it gets easier because the set of roots has a limit set, and the limit set is much easier to describe than the roots themselves.
The Riemann hypothesis deals with zeros of a transcendental function.
Yeah, but it doesn't deal with the zeros of all the derivatives. Yeah, if you look at the function and all its derivatives and all those zeros, you actually get something a little easier. There's a book by Whittaker, the son, not the Whittaker of Whittaker and Watson, Interpolation on the Integers, and he has some really nice results there about this sort of thing.
What is? I didn't know there was a Whittaker the son.
I think that's right. I mean, I haven't checked it recently.
Well,
Okay.
still waiting for some volunteers. We have 3 speakers, 3 different people speaking, starting in about 3 weeks. But next week and the week after, there's a rare opportunity for someone to give a talk who might wish to do so.
I just submitted a paper for the Fibonacci conference in Sarajevo, and I'm busy working it out, but I don't know if I'll be ready in a week or 2. Maybe in a week I'll be ready.
It's not physically in Sarajevo.
I asked Steve Miller, he said, too many conferences are being canceled, and it is there. I said, well, I can't come. He said, because I observe Sabbath, I'd have to come 2 weeks instead of just 1 week. I can't come on, I have to leave on Wednesday. So if the plane gets delayed, I don't, wind up driving on Saturday. So he told me that I should apply for funding. And I said, okay. And I submitted an abstract on something I worked. Very nice. It's a system of 4 recursions. So it's sort of nice. And I generalized something.
Let's see. Who's likely to invade Sarajevo?
It's a very nice place. I mean, it's as likely to be invaded as Ukraine, but Ukraine got invaded. The water snow, I remember their ads. We've been having the Fibonacci conference in Sarajevo for 3 years. And every time we have it, 2 years ago, we had to make it virtual, and last year we had to make it virtual. So the organizers said, well, we're going to keep our promise there. They have nice advertising. They do water rapiding. Unfortunately, it's on Sabbath, but there are a lot of funds there. Whenever you go to a Fibonacci conference, you always have at least 2 tours. So I haven't seen anyone in a while, so I really look forward to just seeing all my colleagues. There are about 20 countries there.
So in about 5 weeks, Georgios Petrides is going to speak in the seminar. Physically, he's coming to New York. So I've been told that it is possible to actually have a seminar at the Grad Center, which is live on Zoom as if it were anywhere else. So
we're having someone from California talk tomorrow at Towson on, I don't know, some graphing theory thing, some topology thing. So I think talk's virtual, but we'll be in the room and you can log in by Zoom.
Right. So it's just a question of what is the machinery available in the room to do that. And I know it's done at the Graduate Center somehow. I just have to figure out what the word somehow means.
Yeah, they have this fancy thing in the big, I think it's 4214, right, in the big room. And it's like, yeah, and then it's done, they just do it through magic using that.
There's something at the Grad Center called OWL, O-W-L.
Yeah, that's what it is.
I have no idea what it stands for. What it
Actually,
is.
what happened at Towson, we have this technology, and the person from the computer center said she would help, walk us through. And she personally came down and walked me through. And I said, why don't you just give a seminar? She said, it never works. You give a seminar, no one knows what they're doing. So she personally went down and I tried it out. And about a week or 2 later, I had a problem. Something was left out of the instructions. So they improved the instructions, but I lectured in a room during Zoom in fall of 2020. And the technology caught me and the Blackboard, and my students were on Zoom. It was sort of very nice. Anyway, my students are now in the room with half of the mass, so.
Okay. Kevin, are you there? Kevin Johnson. We actually have a faculty meeting going on at started at 3 o'clock. So, all right. Okay, everyone.
Okay.
Stay well.
All right.
If I finish by next week, I'll have something for 2 weeks. I'll let you know.
Let me know. All right. Bye. all.
Thank you.
Bye, David.
Be well. Bye.